Okay, guys, welcome. Today we're going to talk about the power rule for logarithms. So this is a shorter video. What we're going to talk about regarding the power rule is we'll talk about how to use the power rule formula for logarithms. And then we'll also do a cool application where we talk about radioactive decay using half-life. And then we'll talk about how you can actually evaluate logarithms in your calculator using what's called the change of base formula. Okay, so first of all, let me explain the power rule for logarithms to you. And the idea there is that if you have a logarithm of something to a power, it's equivalent to write this is t times log base b of y, right? And if you're curious, you can ask me, and I'll sort of show you the idea of why this is true. But it's related to, not quite the same, but it's related to the fact that if you have like a power to a power, that what do? You multiply the exponents, right? So sort of in this way, you have a power leading to multiplication, right? And that's sort of what's happening here. You have y to a power on the left side, and that's leading to multiplication. So it's sort of related to that sort of idea. All right, but anyway, let's go ahead and we'll do an interesting application, right? So of course we want to find how many digits does 3 to the 5,000 have. Now the idea here is that we can use a common log and that will help us figure out how many digits we have here, right? So if I want to look at 3 to the 5,000, this is an extremely large number. And it would take way too long to actually count the digits, right? So what you can do instead is that I can find the common log of 3 to the 5,000. Right? Now the idea here is that I can move this 5,000 out front, and that's equal to my original problem, right? My 5,000 times log of 3 now. Okay. Now if I find log of 3 on a calculator, I'm going to get 5,000 times 0.4771 something, right? Now if I multiply this by 5,000, I get that this is 2,385.61 roughly. Okay, now what does this mean? Let's think about this for a second. If I have a common log of 1, right, we know that that's 0, right? Because that's saying that 10 to what power gives me 1, and of course that means that x is 1, all right? If I want log of, say, 10, that's 1, right? Because this is 10 to the x is equal to 10, right? If I want log of 100, that's 2, because if I solve 10 to the x is equal to 100, I get that x is equal to 2. So hopefully you're sort of seeing the pattern here, right? This has 1 digit, and my value is 0. All right, this has 2 digits, my value is 1. This has 3 digits, and my value is 2. So if log of this is equal to 2,385.61, then that should mean that I have 2,385 digits. Right? I just sort of round down there. All right, and that's sort of the idea. All right, so that's an interesting application there. Now, a more realistic application of this power rule for logarithms is something like this. So I have log base 7 of y is equal to 8.6. All right, and with that information, I want to find log base 7 of square root of y, only using that information. Well, I know that this is log base 7 of y to the 1/2, and by using the power rule, I can write 1/2 out front, log base y, log base 7 of y, right? But again, we know that log base 7 of y from the given information is 8.6. So this is 1/2 times 8.6, so this should be a 4.3. All right, and that's the idea. So the power rule allows you to do this problem without knowing actually what y is. Okay, now I want to look at an application of this power rule for logarithms, right? So if you have some sort of radioactive isotope that has some half-life h, we can model the number of atoms currently present in that isotope, where A0 is the initial amount, right? T is the amount of time that's passed, and H is the half-life. All right, so we can use this information to do that. All right, so let's look at maybe not the most cheerful problem, but we'll look at a problem nonetheless. So we're supposing that a cat skeleton found in an old well has a ratio of carbon-14 to carbon-12 that is 61% of the corresponding ratio for living organisms. We want to know approximately how long ago did the cat die, okay? So we're told that the ratio is 61%, right? And I suppose that we need to know, so that's one thing that the book doesn't have in here. We need to know the half-life of the carbon. Okay, so again, we want to know, so we have basically that A0, if that were to be sort of 1, we know that the current value of A is 0.61, right? So we have 61% of what we originally had. So we can say 0.61 is equal to 1 times 2 to the negative t over h, and that's what we need to find. We need to find, and of course this would have to be normally be given to you. The book should have had this in there, but it doesn't. So let me see if I can, so the half-life of carbon-14, let me see if I can look this up real quick. So if we try and find this, so let's see. Okay, well, you know, instead of trying to hunt for it, what we're going to do is let's just say that H is, I don't know, let's say that's 5,000 or something. All right, I don't know if that's what it is, but we'll just assume that the half-life is 5,000. All right, so that means that a 5,000 is coming in here. Okay, well, what I want to find is 0.61 is equal to 2 to the negative t over 5,000 and solve that for t. Well, of course, I can convert this to a log equation, and this is log base 2 of 0.61 is equal to negative t over 5,000. Okay, now to get t by itself, all I would need to do would be to multiply both sides by 5,000 of 0.61, and then take the negative, and then that would give me my t value. All right. Now, if you wanted an actual number here, you'd have a little bit of a problem, because if you look on your calculator, you're not going to find a spot to enter a log with base 2, right? You'll find a common log, and you'll find ln, which is a natural log. So to get around that, we can use what's called the change of base formula. And that allows you to change the base of any log, right, to whatever you want. Now, of course, why is that beneficial? It's beneficial because we do have common logs on the calculator. So these are on a calculator, right? So if you want to find a log base b of y in the calculator, you just find log of y and divide it by log of b, where those logs are common logs. Okay, so an example of that would look something like this. We want to find log base 2 of 73.9. Now, if you try converting this to an exponential, you'll have 2 to the x is equal to 73.9. And of course, there's no number that you can raise 2 to in order to get 73.9, at least not cleanly, right? So what you have to do is you need to use the change of base, right? And that says that if you have a log with any base, you can make that into a common log of y over a common log of a. So in this case, I want to find the common log of 73.9 and divide that by log of 2. And of course, if we do this in the calculator, if I do log of 73.9 divided by log of 2, we're going to get that this is roughly 6.208. Right? I should use approximately here because it's, of course, not exact. All right, but you get 6.208. All right, so that's sort of the idea. Okay. One more example that we'll look at is I want to look at the graphs of log base 2 of x and log, just a common log of x on the interval 1/8 to x, or to 8 here, right? This will be the last one that we do. Okay, so let's look first at log base 2 of x. And we'll say this is equal to y. All right, now what does this mean? This really means that 2 to the y is equal to x, right? So if I wanted to plot this, I could just find some values for y and figure out what the corresponding x values are. So I'll do -3, -2, -1, 0, 1, 2, and 3, because I know that that's what's going to work for this interval. All right, so for example, if I plug in a -3 in for y here, I'm going to get 2 to the -3, which is 1/8. Right, and then you can similarly show that if you plug in -2, you get a 1/4, you get a 1/2, you get a 1, you get a 2, 4, and an 8. Okay, so if we plot this on a graph, I'm going to get, so 1, 2, 3, 4, 5, 6, 7, 8, and then I need to go 1, 2, 3, 1, 2, 3. So now if I plot these points, I have 1/8 -3, so I have something very close to the axis. I have 1/4 -2, so I have something like that. 1/2 -1, 1, 0, 2, 1, 4, 2, and 8, 3. So I have something like this. All right, and this is my log base 2 of x. All right, now if I use similar logic for log of x, which of course means that we have a common log, this means that 10 to the y is equal to x. All right, now if I look at some values here, and here I'll just do -2, -1, 0, 1, and 2, because this is you'll see it's going to go off the rails. If y is -2, then I'm going to get, let me use a different color here actually. If y is -2, well, 10 to the -2 is 1/100. If I use -1, I'm going to get 10 to the -1, which is 1/10. 10 to the 0, of course, is 1. 10 to the first is 10. And 10 squared is 100. So now if I plot this, I'm going to get a very different looking graph. At -2, I'm basically on the axis, right? Because I'm at an x distance of 1 over 100. And then for -1, I'm still very close to the axis. Now at 1, I'm at 0 again. But at 10 is when I first reach 1. And I'm not even going to bother with the last point because I'm not going to be able to draw 100 hatch marks on here, right? So I'm going to get something like this. All right, so I get a more sort of drastic curve there. All right, and that is, of course, going to be true with a larger base because if you think about these being inverses of exponentials, right, the inverse of log base 2 would be 2 to the x, which would be something like this. And the inverse of common log of x is 10 to the x, so of course that one's going to be much steeper, right? Right, and that's sort of the idea there. All right, but that concludes this video on the power rule for logarithms. I hope you enjoyed, and I will see you next time.